So again, good morning, everybody. Today is the last day. I have a lot of material, so I will have to make some decision about what to choose the last day. But first of all, let me ask you if you have any comment or questions in relation to what you have heard in the last 2 days.
Yeah, I've given your demo a bit of thought with this particle model.
Which model?
I think you showed a video with some particles.
Particle modeling, okay.
Which came out of a stack. And I had the feeling that at the end of your demo, the whole thing was not behaving very realistic. Because the fume spread it out a bit. But I also think this is due to a problem, which is, well, I think you have it. Yeah, exactly that. I'm not sure whether the spreading is very realistic.
Yeah, actually, so in your opinion, the movement of particle is not very realistic. And which particle are you talking about? The red one, very attached to the ground, or the other color of elevated particles?
I think all of them. And I think the problem is due to that you might have only one station.
Okay, yes.
Which is giving you the wind.
In this particular case, I have only one station. And you see and that's my choice, because the concern here, the emission is over here. You see my mouse, and the person complaining about the impact of the plume is here, very, very close. It is, I think, 1/3 of a mile. So 600 meters. So in this situation, you don't need a multiple meteorological station. Even
listen to this guy.
Hello?
Oh my gosh.
Hello?
Yes, I'm still here.
Okay, very good. So I heard a voice. I don't know if it was a question or
wasn't
whatever.
Me, no.
Okay, very good. So yes, I have only one meteorological station, and the other meteorological stations are miles away. So they do not have the capability of affecting the plume. So what seems to be an irregularity is actually just the fact that I have only one station. So the plume is representing exactly the dispersion. And if we had additional station here within a mile, I would have used them and triangulate over the station, and the plume would have looked slightly different.
So I think the answer to my bad feeling with that is simply, this is a model and not reality, and you simply do the best you can.
This is the best that we can do, with one station. And it should be the reality, because we don't expect the meteorology to change very much over a 1 or 2 miles distance.
Yeah, that's just what I thought. What you are measuring is local wind, which is influenced by local disturbances, local eddies, and so on.
Yeah.
And if you apply that to the complete fume, you will not really model the reality. So it depends a lot on how much deviations you have in your measurements.
Well, this is true for everything. It's true for the wind.
Yes.
It's true for the emission rate. It's true for the vertical motions that are, it's true for the turbulence parameter. All these models are approximation of reality, and therefore you should be very careful in analyzing the result. In fact, when you present the result, you should always talk about uncertainty and uncertainty bands. So how certain we are that the plume is going exactly in this direction? No, we could have a 10-degree difference between simulation and reality. But you see, in this particular case, the person complaining for plume impact is here. So even if we, and I have this problem when I presented these results to the jury, I was asked how confident you are on the results. And my answer was, I'm very confident that there is no impact in the plaintiff's location, in the location here. Very confident. How confident I am that the plume is exactly going along this trajectory and not deviating by 5 or 10 degrees? No, I'm not confident about that. But I feel that the probability of the plume impact at this location is very, very low, if not zero.
Okay.
Very good.
Okay, so you brought an important point there, I think. You have to be clear about the uncertainties of your model.
You have to be clear. Well, this is true for any calculation in science. You have to think about how reliable are my data, what is the possible deviation or error, plus minus 10 degrees, for example. This is what I say most of the time, that plus minus 10 degrees is a reasonable one. I hear some background noise, so perhaps if you don't speak to me, you want to turn the microphone off to avoid interference. But okay, so I'm glad about this question because I was able to clarify, I think, an important point, the reliability of our data. And they are in the context. If we have had people complaining much closer to the plume, it would have been a different opinion. But in this particular case, for a short duration of the release and for the meteorology that I have analyzed, I feel quite confident that this person was not impacted by the plume. Other could have been in other location, but not this particular one. Very good. Let's see if there is anything on lesson 2 that, or yesterday's lesson that I want to elaborate. I just want to mention, to repeat, the history of development of air pollution modeling, which has a logical way. We started with a simple equation to describe the entire plume. This is the Gaussian plume model, which is still used in the preferred EPA model, AirMod. So we started with a relatively simple equation that describes the entire plume for 1 hour at a time. Every hour is a new plume, and the old plumes are forgotten. They don't affect our calculation anymore. It was an empirical approach. It worked relatively well. It has many theoretical limitations, but again, it worked relatively well. And then we started thinking about how can we remove these major limitation of the Gaussian plume model. And the next step was the puff. Instead of having a single plume for each hour, we have a generation of puff, maybe every 5 minutes. So from each source, we have a new puff generated every 5 minutes. And this really has improved the theoretical capabilities of our modeling approach, because now we are able to deal with dynamic simulation instead of static simulation. Now we are able to incorporate the change of wind direction with time, every 5 minutes, for example, if we have the data. And we are able to deal with conditions like calm and low wind that are not simulated correctly by the Gaussian plume model. So the next step was the development of Gaussian puff models, and in particular the CalPuff software produced by the EPA. So this was a major improvement, more theoretical than practical, because today we still use air mode more frequently than CalPuff, but it was a major development. Then the next development was later, when we said, we have powerful computers. Why can't we generate thousands, tens of thousands, 100,000 particles? We call them particles, but actually they are tracers. They are mathematical points that we use as tracer of the plume. So we generate thousands and thousands of particles, and we can follow the plume with a much better resolution. And that was the particle modeling which came out in the last few decades. So you see, all the research has been an effort to improve the resolution from a simple straight line plume to a series of puffs, and then finally to a series of particles. All this evolution has dealt with transport and diffusion. If we have problems with chemistry and photochemistry, unfortunately, we have no choice. We have to go to grid models, which are much more time-consuming, much more complex. But again, if you want to do the chemistry and the photochemistry, you have no choice. And we talked yesterday about the grid model, and in particular, I mentioned CAMEX, which I believe I recommend as the most cost-effective choice if you want to simulate photochemical smoke. Okay, so I wanted to put these things into a perspective, so you understand the history of evolution of modeling, and which follows, of course, the history of evolution of computers. Now we have capabilities that 20, 30 years ago we did not have. Let's see if there is anything about yesterday. Air quality management, I skipped it, is something that I'm going to send you the PowerPoint presentation, but for this course, as an introduction to air pollution modeling, I think I'm going to skip it for now, at least for now. I would like to talk about modeling of adverse effects, but let's not do it now. Let's try to do something later. So let me open
Hello, Prof.
Hello?
Yes, sorry,
Hello?
before you proceed. Hello, yes.
Yeah, so,
Can
okay,
you
go
hear
ahead.
me?
Yeah, I can hear you now. Go
I
ahead.
said, yes, before you proceed, sir, I would like to, yesterday you talked about, on slide number 45 yesterday, of what you presented. You talked about the short range dependence and long range dependence of modeling.
Yeah.
So I know of short range and long range dependencies as statistical properties. For example, if one is dealing with ARIMA modeling, that is regarded as short range dependence. And when one is dealing, for example, with ARFIMA, fractionally integrated ARIMA modeling, that one is long range dependence. So I would like to know, what is the difference between what you presented yesterday with these long range and short range dependencies?
Okay. Well, the ARIMA models are statistical models dealing with time series, the analysis of time series. And ARIMA model can be used both for all sort of data. So it's a little different from the topic here. But short range simply is just a few miles, and long range may be 100 miles. just to give you an idea.
Okay.
In air pollution modeling, we talked about short range. I would say, for example, if you have if you use air mod is designed for short range, maximum 50 kilometers. But if you do a simulation of a Chernobyl release of a radioactive plume going all over Europe for hundreds, thousands of kilometers, that will be long range.
Yeah. Okay. I understand, sir. Thank you.
Very good.
Thank you.
So let's open day 3 and see what we have here. Okay, model of adverse effect and case studies. Okay, so a few words on available and recommended software. We already talked about the EPA models and the Scrum website. That is my first recommendation on how to choose a model. Again, don't forget, all the EPA recommendations and guidelines are related to the use of models for regulatory purposes. But it is a good idea to start with the EPA guidelines and recommendations. And then, of course, if your problem is not regulatory modeling, you have much more latitude, much more options to choose different approaches. But I think the EPA recommendation are always a good start. In the best resource, as I told you before, is the Scrum website by the EPA, and there are several sections on air quality modeling, modeling application and tool, guidance and support, a set of meteorological data set, information about conferences and workshops that were performed organized by the EPA, report, journal articles. You find everything here, a lot of useful information. The most common air quality models, according to the EPA, but we agree 100% with this statement, are dispersion modeling, like air mod, like those that you have seen so far, photochemical modeling that we have discussed yesterday, so grid models, receptor modeling that we have briefly said something on the first day, and we may be able to say a little more if we had the time today, which is a statistical approach in which you just use measurement of particulate matter to try to understand where these chemicals are coming from. So these are the main groups: dispersion, photochemical, and receptor. Let me fix this. Okay, so we have discussed these things yesterday. There are other preferred recommended dispersion models. I'm not going to spend time on this because really today AirMod and CalPAF are what is really useful. However, if you have heavy gas, dense gas, heavy gas clouds, sometimes DEGADIS may be useful. Is not, I don't know how much is, it's an old model, but it's still used for describing the process of heavy gases. So this may be a choice sometime if you have a particular accident, for example, in which in which a heavy gas has been generated. ISC is old, nobody uses anymore. SkyPath. SkyPath is still used today. I prefer CalPath. SkyPath is more complex and less popular. But again, for some application, SkyPath may be better. I'm not 100% sure about this. I've seen people using SkyPath. I use CalPath, and that will be my recommendation. But they are both path models, of course. Photochemical modeling, we discussed them yesterday. Nothing new. We talked also about the most comprehensive model, which is the CMAC model developed by the EPA, still under evolution. But again, my recommendation, I repeat, is CAMEX. Available receptor model, I already told you that if you want to start with receptor modeling, the chemical mass balance model is the way to start. And then you can move to other more complex methodologies, but the CMB is really the best choice at the beginning. So I repeated a few things. We discussed them before. Scrum website, I already show you. Okay, other models. In addition to those recommended by the EPA, there are many other models that are available in the literature, but they are research prototypes. These are models developed by scientists working at universities or consulting company, and they have developed their own software for special application. And this software may be similar to the model recommended by the EPA or different, but it is worthwhile to give a look to what other people have developed, especially at universities. So there are many pieces of software that you may consider in the future if you continue to work on air pollution problem. In particular, however, I want to mention the software of two companies. One is ARIA, is a French company with offices in France and Italy, has been recently purchased by Suez, which I believe is a Spanish company. But ARIA scientists have developed several models that are similar to the EPA model, but I would say more complex. Both meteorological model and dispersion model. So you see here a list of all the indoor software, the risk assessment, the simulation in the cities, indoor. So they have a lot of, we call it proprietary software. It's something that they have developed internally, and they use it all the time. So this is a very high reputation company that can be of some help for some particular studies. Another company that I want to mention is what happened here?
So just Suez is a French company, just for your information.
Suez is French. Okay, I thought it was Spanish. Thank you for the clarification. Yeah. Let's see, Suez. I'm not checking, I believe you, but I just opened it up. Okay. Very good. Yeah, it's you're correct. It's a large group. Okay. Let's go back to the second company of consultants that I would like to mention, in addition, of course, to my company, which you already know, EnviroCom Consulting is my corporation, and I do consulting too in air pollution, especially accident and especially litigation. But the second company I want to mention is EnviroWare. I work with them all the time in joint projects, and of course they use the models of the EPA, but they also have their own software, their own meteorological software. They have wet plume for cooling plant, a software to simulate the plume from cooling plants. They have lap mod. We already talked about this. The particle model that they give for free. They are located in Italy, but they work all over Europe. So these are the three companies, mine and these other two, that I want to you be aware that if we can be useful in the future to you, of course, we are always ready to help. Odor modeling. This is something that is quite important because in many cases, the main concern is not really air pollution and getting sick and getting cancer. In many cases, the major complaint of people is odor. For example, if you live near a paper factory, there are odor problems with H2S. If you live near a refinery, there are problems. If you live near a farm with thousands of cows or a slaughtering facility, there are odor problems. So, and the list is very long. But in many cases, what we are asked by our client is not just to simulate air pollution, but to simulate the odor impact of air pollution. And this is really opening a new series of studies and analysis and challenges. There are chemicals that have a bad odor. For example, mercaptans. Mercaptans are the chemicals that are added to natural gas. Natural gas is odorless, but intentionally we add a little bit of mercaptan. So if you have a leak of natural gas in your home, you can smell it and you know that there is something wrong, and then you have to do something. So it's a safety problem. H2S is the most common chemical that is very can be very very impacting from the odor point of view. Even very small amount of H2S, you can smell it. In the literature, you find all sort of threshold levels for H2S. And there are many books showing experiment with people that are given a certain concentration of H2S, and they have to say, well, it's bad, is very bad, a little bad. So there is a lot of empirical literature on the human impact of these odorants. That's how we call this chemical that have an odor, odorants. But it's very confusing. If you work in the future in this field, don't be surprised to find a lot of confusion on the odor thresholds. Some people can smell H2S at 5 ppb part per billion. Other people can smell it at 100 ppb part per billion. So it's very difficult to establish whether or not we have an odor impact, because it depends on the person. Odor is a human sensation. we try to measure it, but it's not like measuring a concentration, which is a physical value. 10 ppb of H2S is a measurement. An odor impact is something that can vary a lot. Let's see what they say here. There are several publications with reference guide to odor threshold. And you find all sorts of values. For example, again, for H2S, I can tell you that you find studies with 5 orders of magnitude difference, 5 orders of magnitude difference between odor thresholds at different locations and different people. So you have to be careful. But basically, the problem, conceptually, the problem is simple. We want to run our models, calculate concentration, for example, of H2S produced by a refinery, and then establish the odor impact of these concentrations. What is the challenge here? Well, the challenge is that in many cases, H2S emissions rates are not known. Other chemicals like SO2 or other carbon monoxide from a car, other chemicals, we have a decent understanding of the emissions. But for odorants, sometimes we have absolutely no idea. For example, landfill. A landfill is emitting H2S, and people living near a landfill often are complaining. But to calculate the emission from landfills is quite difficult, because it changes with time and location. It changes very much with time and location. I've been working in several landfill projects, and it's always a big problem. There are landfill models that may give you an estimate of the emission rate, but even this model have a lot of uncertainties of orders of magnitude. So this is a challenge. The second challenge is that, which is even more important than the first, that some odors are too complex. We are not talking about mercaptans or H2S. We are not talking about chemicals. We are talking about a chemical soup. For example, the odor complaints from agricultural activity, from animal farms, it's impossible really to know which chemical is impacting people. It's a chemical soup. And so it's quite a challenge to measure it. And even after you measure it, it's a challenge to understand which of the chemicals inside the chemical soups are those that are really causing the problems. Another complication for odor modeling is discussed here in this section. This is a chapter that I'm going to send you, and it's quite useful at the beginning to have an idea of, of what odor modeling is and what mathematical tools we can use to study this. First of all, can we measure odor? Well, of course, we can measure the concentration of chemicals in the air, as I mentioned before, for H2S or for some chemical soup. But can we measure actually the odor as a unit? And the answer is yes. Yes, you can grab, for example, a certain amount of air. Then you can take this air to the laboratory, and you can dilute this air and can give, after this dilution, you can give a test to a panel of people, 5, 10 people, And then they can tell you, yes, I smell something. It was unpleasant. It was slightly unpleasant. Yes, I smelled, the smell was very strong. So you can have a group of people, a panel, that gives you an idea of the intensity and the characteristic of the odor. It's called a dynamic dilution olfactometer test. And let me give you also a definition of, these are the 5 parameters that we can evaluate the character of the odor. For example, fruity, musty. These are typical words or description. The hedonic tone, if it is pleasant or unpleasant. For example, a perfume is generally pleasant. A coffee smell is generally pleasant. The smell of fresh bread is generally pleasant, but any odor above a certain level of intensity may be a problem. For example, I don't like, if I am in a theater, for example, to smell a strong perfume odor from a person near me. It's a small amount is fine, but a strong perfume indoor is not pleasant for me. So the hedonic tone measure the pleasantness or unpleasantness of the odor, the intensity, how intense it is, and the concentration. The concentration, which is the big challenge. That's why we send samples to the lab to have a panel of professional people to give you an opinion of this type of odor. There is also an instrument that you can use in the field. It's called the field olfactometer, because you can take it with you. You take this instrument to your area where people complain about odor, and when you smell an odor, you collect air inside this instrument, and then you dilute with fresh air. You dilute by a factor of 2, by a factor of 4, by a factor of 8. You continue to dilute until you don't smell it anymore. At that point, the number of dilution is proportional to the intensity of the odor. Is it clear? You start with odor in a certain region. You grab a sample of air, polluted air inside here, but this instrument allows you to dilute the polluted air with fresh, clean air. So you dilute 2, 4, 7, and on and on and on, until you don't smell it anymore. So the original intensity of the odor is proportional to the number of dilution that you have done. So this is a simple instrument that allows you to measure the intensity of the odor at a certain location at a certain time. Another big challenge with odor is the averaging time. And I'm going to show you a picture which you already seen with different color. You remember when we started talking about the Gaussian model, I show you that the instantaneous plume may be quite irregular, and the concentration of the instantaneous plume can be quite strange. But hopefully, when we average over an hour, the plume concentration tends to become a bell-shaped distribution that can be described by a Gaussian equation. And most models that I've shown you in this course deal with average concentration. For example, the Gaussian model R mode simulates 1 hour concentration. CalPath typically is used to simulate 15 minutes or 60 minutes average concentration. But with odor problems, we are not dealing with average concentration. Odor is an instantaneous sensation. So the concentration that are important are not the 1 hour average. They are the instantaneous or maybe 5-minute average. We have to go down to 1 minute, 2 minutes to represent what is really the odor impact. So it's another challenge. I cannot use a model that simulates only hourly concentration like AirMod, or if I simulate hourly concentration, I need an algorithm that tells me if I simulated 100 ppb over 1 hour, what will be the maximum during that hour? The maximum instantaneous concentration. Because odor studies require the evaluation of the maximum instantaneous concentration that could have caused an odor. And there is another plot. Okay. There is another plot here that explains you the challenge here. Typically, if we measure the concentration in the air of any chemical, but in this case, we are dealing with odorous chemical. What we see, if we measure minute by minute, if we have an instrument with a high resolution capable of measuring minute by minute, typically we see something like the blue line over time, going up, going down, going up, going down, and so on. If we take the mean over 1 hour, we tend to have something represented here by the green line. This will be the mean. And the model will simulate, like AirMod, the model will simulate 1 hour average concentration, so the mean within the hour. But the mean is not the value causing the odor. The odor threshold may be the red line, and anytime the concentration is above the red line, I smell something. So you have to be very careful about the use of the output of the model, because odor problems are caused by the maximum concentration, the maximum 1 minute or 5-minute concentration, and not the mean. So this is a further challenge that we have when we do odor modeling. Let me see if there is any other issue that I need to underline. This is a list of sources of odor: composting facility, wastewater treatment plant. I visited once a wastewater treatment plant in Washington State. I almost fainted. It was really, I think I was measuring H2S. I measure 1,000, 2,000 ppb of H2S. So that was quite a very high value. Cement factory, landfills. These are the type of plants, and all agricultural activities. These are the type of activities that generally cause odors, and refineries. How have the government agencies reacted to the odor challenge? Well, many states in the United States have established odor standards and criteria for certain chemical. For example, many states like California have a standard that should not be exceeded for hydrogen sulfide, which is 30 parts per billion. My experience is that I can smell something above 10 ppb, but just minor. So I think this is reasonable, but okay, you notice that the standard is for 1 hour average. I just told you a minute ago that odor is not a problem that can be described by 1 hour averages, but sometimes you have to, it's difficult to measure instantaneous concentration. So in establishing the standard, California has used, for now, they have used the 1 hour average. So if the 1 hour average is 30 ppb, that means that at the instantaneous level, probably you may have 50, 60, even 90, it depends. So these are the type of values that are considered a problem, a challenge for odor. Other states have defined different standards. Some states define the standard as 8 times or 16 times or 7 times the detection level. So they don't care about the chemical that are producing odor. What they say, for example, Kentucky says that if the odor that we measure, whatever it is 7 times, is greater than 7 times the minimum odor threshold, then we have an exceedance of the standard and we have a violation of the regulation. So these are the two approaches that are used. Either the standard is for a chemical, for a particular chemical like hydrogen sulfide or methyl mercaptans, or the standard is based on the detection value. It is generally considered that if an odor, even a pleasant odor, if an odor is 5-7 times greater than the basic odor threshold, that odor is offensive. Odor modeling, well, odor modeling more or less is the same as dispersion modeling, except what I mentioned a minute ago, that in some way you need to understand what is the maximum instantaneous value within the hour and not just a mean. So there are factors that are used. For example, a typical factor is 1.6. If the model simulate hourly average concentrations and the concentration is 100, the maximum concentration during the hour was 160, a factor of 1.6. There are several factors in the literature, but typically I use 1.6 in my studies. And then, of course, you can use all the models that we discussed before, plume model, puff model, particle model, to calculate the concentration. But again, once you finish and you calculate the concentration impact, you haven't finished. The next step is to evaluate the odor impact. And that is a challenge. Okay, this is the peak to mean ratio that I discussed a minute ago, the factor of 1.6. This is very important. The model is giving you the mean over the hour. You need to know the peak during the hour. So there are several formulations that I'm not going to spend much time about it, but there are several formulations that allow you to calculate this factor. Perhaps 1.6 is a good initial choice. These are the these are some peak to mean factor used in the literature: 2.2, 1.8, 1.3. You can find all sorts of choices. Okay, so this is what I wanted to tell you about odor modeling. You will use the same models we discussed before, but then you have to be careful in interpreting the results and performing an odor impact assessment. I'd like to show you a few case studies. 6:50, so we have another. Unless there are comment or question on odor modeling or other issues, I can go ahead for another 10 minutes. Any question? Very good. So I'd like to show you a few test cases of projects, mostly projects that I have done. So I can explain better these case studies since I was heavily involved. And they may serve you as an example on how to proceed in your future air pollution projects. It's not, when you work on a real case, it's quite different than just studying models and mathematical equations. And when you work on a real case, you have to be very careful and use common sense to be sure that you do the right thing, and especially you present your results in a way that is fully scientifically acceptable. We already talked about presenting the result with the uncertainties. Instead of giving, oh, my result is 53. No, my result is 53 plus minus 10, because there are uncertainties. And there are many rules that you learn in working on real cases that you have to be very careful about what to do, especially if you work in litigation where you are under a very strong control and checking and challenging. Your work needs to be bulletproof, as we say, because in litigation you are challenged by the other side. So a few case studies. I'll try to tell you some lessons that I've learned that may be useful to you in the future. I work on many fires, plumes from fires, and they are quite difficult because a plume from a normal stack has a behavior that is relatively well known. We can look at these plumes in the field. There is an initial phase, the plume rise. The plume is moving up and bending. And then there is a second phase of the horizontal plume expanding. And then finally, the plume is touching the ground and diluting with distance. This is a well-known behavior. But for fires, yeah, you see the plumes from fire, but they are different. They tend to go higher because they are hotter. And sometimes a large fraction of the plume from the fire is remain trapped aloft, doesn't come down. So if you use the standard Gaussian model, Gaussian plume or Gaussian puff, you have to be very careful because The Gaussian model will open the plume and the plume touches the ground. Sometimes with fire, that doesn't happen. Or it is only a small fraction of the plume that touches the ground. Most of the plume remain there, aloft, and you can see it. All the dark plume a mile above, or 1.5 kilometers. So modeling the plumes from fire is an extra challenge, and you have to be very careful. I've seen a lot of people making big mistakes in simulating fires. The other problem with fires is that everybody sees the plume, everybody. So everybody gets agitated and scared. That doesn't mean that the plume is impacting their location. So whenever there is a fire, thousands of people around our industrial plant are seeing the fire, are worried, are scared, and may sue the company for the fire impact. But actually, maybe only a small number of people that were really impacted by the fire and inhale the products of the fire. So you have to be very careful. This is an example of a big fire in Los Angeles, a refinery fire, in which 5,000 people, you see all these dots in this map, these are all the people that sue the refinery and sue for damage. And it was very important here to distinguish between the people who could have smelled the plume and people that were just scared for the fire. Because if you are just scared, you may be paid, I don't know, I'm just guessing, $1,000 because by the refinery, because of the damage that you sustain, the being scared. People that inhale the plume, they may be paid, I don't know, $10,000 because they were in the middle of a plume. And people who went to the hospital because they claim health impact due to the plume may be paid much higher amount. So in this case, air pollution modeling is a critical tool to establish how much people have been damaged and how much they should be paid. We are talking about 5,000 people, so at the end of the day, we are talking about tens of millions of dollars that may be involved in a case like this. And this was my simulation. Using the best available science, I was able to establish that the plume impacted this area. And if I remember well, my plume was further enlarged. They added a 10 degrees plus minus of uncertainty. So all these people were paid more, I believe. Generally, I'm not involved in the payment phase of a case. I'm just a scientist. I just do my own science. But my understanding is that my plume results eventually were used to settle the case. And so it was very important to simulate the plume as good as I could. So there are some lessons here that can be learned in the future. If you study accident, you have to be very careful. Another project that completely different, because the first one I show you was just a few hours impact, just a few hours. Here we are talking about a lifetime impact, a lifetime. This is a very famous litigation case, has been in all the newspapers, and many books have been written, more or less honest book or accurate on this case. This is a famous Beverly Hills city, which has a very famous Beverly Hills school area in Los Angeles where, you know, many important people, even actors, have studied when they were teenagers. So it's a quite famous school. And very close to the school, there is an extraction well, an oil extraction facility. So whenever you have oil extraction, of course, you may have some leaks and some emission of benzene, formaldehyde, chromium-6, PEH, dioxin, and so on. So in theory, all the students here could have been affected when they were studying in high school in Beverly Hills, could have been affected by a certain amount of concentration caused by this oil extraction. We are talking about a lifetime exposure. So for each person, we have to reconstruct the lifetime and the lifestyle. What did they do? Where they were sleeping, where they were working, if they were working, where they were studying, where they were running. Here there is a football field nearby, what they were doing typically. So for many people, we have to establish a lifetime scenario of exposure to chemicals. And of course, we are in Los Angeles, which is a very polluted city. So all these lifetime scenarios are affected by emission, not just from the field here, but from other sources. Okay, I see that we have to have a break here, so I will continue. I gave you an introduction. I will finish when we restart at 7:10. Thank you. Very good. So let's start the second lesson for today. You are all there?
Yes.
Yes.
Very good, very good. So let me finish this description of this project that was quite a challenge because we had to reconstruct the lifestyle of 20, 30 people chosen as representative of the population, students and neighbors, and establish decades of possible exposures to chemical, both those emitted by this oil extraction facility close to the school and those chemicals that were normally inhaled because you live in a major city like Los Angeles, especially benzene is quite common and quite high. So we had to discriminate from what was inhaled due to emissions from the extraction facility and other chemicals from the entire city, and establish whether or not the chemical inhaled from the extraction facility were dominant. So it was quite a challenge, and we needed modeling to do that. And we simulated all the emissions that we could estimate historically from a long period of time. And of course, you know, the more you go back in time, the more uncertainty there are in the emission estimates. So it was quite a challenge. And we were under a lot of pressure because this was a very famous case. All the newspapers and TV channels were talking about this. So it was a big pressure case. And at the end, we produce a report. And in this case, my client allowed me to make the report available to everybody. So if you want to see a typical work on a real case, or a real air pollution case in which we have used modeling and other techniques, you can give a quick look to the entire report, which is available on this site. Another example, well, this is not an example. This is a presentation. I prepared some slide talking in general about the challenge which I faced many times in my professional life when I was asked to do accident reconstruction. An accident is a short-term release, a few minutes or a few hours, or a few days. And we need to understand what is the impact of these chemicals emitted from the accident. By definition, an accident is a challenge because it's difficult to estimate the emission rates, very difficult. For a regular emission rate from the industry, we know their emissions, more or less. We know how much fuel they burn. We know how they burn it. We know what is emitted from their stacks. Sometimes we have a good estimate also of the fugitive emissions, those emissions that are not sent to a stack, just leaks. But for accident, the first challenge is to understand how much was released and which chemicals were released. Example of accident, Seveso accident, 1979. This was a major accident in northern Italy with a release of dioxin, TCDD. That was really a big problem of contamination, because then the dioxin deposited at the ground and houses remain contaminated for years. Nobody died, but a few people were sick, as far as I remember. Another terrible accident is the Bhopal release in 1984. Thousands of people died. This was really something really bad. And if I published a paper on Bhopal, which I think is mentioned somewhere. And we were able to establish that it was really a series of problems that coincide at a certain time. It was bad, but it was also bad luck. It was very unusual meteorological condition during the release. With different meteorological conditions, the situation would have been much better, but it was unusual release at an unusual time with unusual meteorological condition. Everything was combined to make the worst possible impact. Another accident is the Chernobyl radioactive release in 1986. It was I was in the Soviet Union for a conference a month after the release in May. I was in Leningrad for an air pollution conference, presenting a paper, and no Russian scientist was aware a month later about this accident. It was quite strange. I think they knew, but they didn't want to talk about it. But many people really didn't know. It was really a cover-up for several days. And then even when they admitted that they were the reason for the radioactive release, this admission was done on international level, but at the national level, people didn't know. People didn't know. So these are just three examples. I'm sure you know about them. And many scientists have spent a lot of effort simulating the plumes that were released from these accidents. The atmospheric dispersion calculation are relatively easy, but there is still a lot of uncertainty on the emission rate. So what can we say about air pollution accident? Well, the first thing we can say that they will happen. Many times when you talk with industrial people and try to say, well, can we prepare for a possible accident? Their attitude, no, our companies manage very well, it cannot happen. Well, actually accidents will happen, and they are mostly due to unexpected multiple failures. These are the key words. It's never one failure that cause a big accident. It's a combination of multiple unexpected failures, and sometimes failure 3 is caused by failure 2. So people think, oh, failure 3 may never happen. Yeah, may never happen in normal condition, but if there is failure 1 and failure 2, then failure 3 may happen. So it's a combination of unexpected things. When accidents happen, we need preparedness and response. We already talked about this. Preparedness is very difficult. Well, it's certainly easier than the response. So preparedness is difficult, but it's possible. Emergency response is very difficult and most of the time impossible. Because as I told you before, in a few minutes, the plume will be out in the community. We are not talking with water contamination that may take a longer time to impact a residential area. We are not talking about groundwater contamination that may take years to contaminate areas of interest. We are talking about air pollution, which in minutes will be in the community. So what we do most of the time is post-accident reconstruction and investigation, which is not easy, but is possible. A week after, a month after, sometimes 2 years after, we do post-accident investigation. And in the United States, of course, there are also litigation problems and litigation activities associated to any major or even minor accident. A few words about litigation, because some of you may be involved in litigation in the future if you continue to work on air pollution, especially in the United States, but also in Canada or Europe. Litigation is quite interesting. I enjoy doing part of my work, maybe 30% of my time now is spent on litigation consulting. It's quite interesting, but you have to be very careful. If you as a scientist work in litigation, you have to be extremely careful. And because it's not enough to be a good scientist, to be a good litigation scientist. It's not enough to be careful, not making mistakes, being honest. You have to know the environment you work with. If you do litigation, you will interact with attorneys. Attorneys are not scientists, and scientists are not attorneys. So we are talking about two different worlds, two different cultures, different skills, different goals, different language. A goal of an attorney is to win the case for their clients. That's their goal. A goal of a scientist is to be honest as much as possible and to apply the best available science. A good suggestion can be that before accepting a project, a litigation project, especially at the beginning, be sure you talk with people, with scientists who have experience in litigation, so you understand the do's and don'ts, what you should do, what you should not do, and use common sense. Basically, you are not an attorney; you are just a scientist. So you work with attorneys, but you have your own culture, your own goals, your own language, and you have to try to help your client, of course, as much as you can without bending science, without changing numbers, without doing anything illegal or unethical. The beauty of accident studies is that it's multidisciplinary. A project is never just air pollution modeling. You need to understand engineering issues. You need to understand physics and chemistry. You need to understand computer modeling and geographic information system. You need to be aware of the adverse effect. You have to have some notion of toxicology, on environmental damage, or economics, or you need to work with other experts that are hired to work with you. So you work with a team many times. Many times an attorney will hire an air pollution modeler, a toxicologist, a real estate specialist, a chemist, an engineer, and there is a team working on the project. And you are a part of a team, and you have to be able to interact with other people. So you have to have some notion of what the other people are doing to be able to interact in a productive way with them and with your client. What is an accident? An accident is something that happens, a fire, an explosion, a leak. You have a plume, all of a sudden, this is on the news. All of a sudden, people are scared. People take the car, they drive away. Sometimes they don't know where to drive. Sometimes they receive reverse 911 calls in which the police call you. You don't call the police. They call you and tell you, stay home, close the windows, turn the air conditioning off, avoid going out, or evacuate. Go here and there to evacuate to a location that is supposed to be safer. So this is a big challenge. What to tell people 5-10 minutes after an accident? What to tell people in the neighborhood? What to do and where to go? It's a big challenge because it's very difficult to know where the plume is going. In this case, it looks like people are driving into the plume in this particular picture. So you have to be very careful. So people are scared. They don't know what to do, and eventually they will sue. They will take legal action against the industry for fear, damage, property values, health, all sorts of activity. So the technical tasks that are required are basically 6. Reconstruct the accident, like what happened, why we had a fire, how long the fire lasted, hours, days, what are the chemicals emitted from the fire or from the leak, what is the emission rate, what is the temperature, the intensity, the size, meteorology. You need to collect all the meteorological data in the area that are available to do the best that you can. Plume path modeling, of course, that's the most important one for my point of view. That's the task generally that I'm hired for. But to do this task, I need the previous 3 tasks to be completed. So modeling will tell you what happened to the plume, where it went, and even more importantly, sometimes where it did not go. Very important. Everything needs to be visualized. Don't forget, probably all this will end up in court. So since the very beginning, you have to think about judges, jury, attorneys, non-technical people that will have to address this. So visualization is the key. If you don't produce results that are easy to understand even from a person that has a high school knowledge, you are failing. If they don't understand you, you fail. It's not enough to be a good scientist. It's not enough to do honest, good science. You have to be understandable. So GIS is very important, Geographic Information System, to visualize on a map on different layers. And finally, other experts, not me, not my group, other experts will have to address the adverse effect of the plume simulated by my team. So you see, it's a sequence of work. One depends from the other. So if the expert doing emission characterization fails and gives me wrong number, all the work that we do here, modeling, visualization, adverse effect, fails. So is a building of knowledge, of scientific knowledge, that you have to be very careful, because an error at the beginning can affect the entire work done by several people with a large budget. Let's talk a little bit more in details about each task. And for plume path modeling, I already told you everything before. We have analyzed all the available models. But a few words on the other task, because you may be involved with this in the future, some of you, and you have to be able to use modeling in a correct way if you work on accident. Accident reconstruction generally is done by an engineer who understands industrial activities and is able to create a timeline of events and to do mass balance calculations and to tell me how much was emitted, which chemical, how long. I need all this information for my modeling. So accident reconstruction is the first step and needs to be done correctly. Emission characterization, again, is the quantitative calculation of the release. For example, I already showed you this, but I'll do it again. I've done a lot of work on flares and emission from flares, which are very irregular. I already showed you this example. This was one of probably my first big accident study in the mid-90s. And our engineer was able to calculate the emission of SO2 and the emission of H2S from a flare during a period of about 10 hours. And you can see that we have 5 bursts of emissions from the flare, huge balls on fire from the flare. So it's not an easy task to model because, for example, if I use a Gaussian plume model, the Gaussian plume models can only simulate 1 hour average emissions. Here, if you do 1 hour average, you sort of cut down these peaks. So this is a typical case where you do not want to use a Gaussian plume model. You want to use a Gaussian path model, and even better, a particle model, which is what I used in this case. And so I was able really to simulate this time variation of the emission. I already show you a video of that. I don't have it at my fingertips. No, I have it at my fingertips. Let's see here. It was shown here. The video of this flaring release with these 5 big high emission rates is shown here. This was my first animation, and this is the flare, and you are going to see a color-coded concentration here. The clock is running. Now is 4 a.m. We have an initial plume. Now it is 5 a.m. We have another big impact of a few minutes emissions, then goes down. And now we are at 5:40, another one. And now we have 6:30, another one. You can see here, if I have used a Gaussian plume model showing hourly average concentration results, would have been wrong. There is no way with hourly averages to show this type of impact minute by minute. It's a must to use. In this case, is a must to use. Where did it go? Okay. In this case, with 5 big emission of 5-10 minutes pollution of SO2 and H2S, I have to use a particle model. If I use a Gaussian plume models, all these phenomena will be averaged and smoothed out. I don't want that. That would not be credible in front of a jury. Very good. The next step is the meteorology. I need to have good meteorology to do my simulation. So I need to collect all the available meteorological and weather data and select the stations that are the most reliable. This is a challenge because every time you go out and collect meteorological data, you find an enormous variation of measurements. This, for example, is the wind speed data collected in a certain region by 7 different stations. They are not too far away. They may be 10 miles away. But look at the difference in wind speed. We have station measuring 2 miles per hour, another station measuring 8 miles per hour. Which one is the correct one for my accident? Okay, I can take an average, I can triangulate, I can use a meteorological model. There are many things that I can do. I can choose the station that is the closest to my accident. I can do many things, but you have to make a decision. So you collect the meteorological data and you find something like that for wind speed. You cannot ignore it. You have to make a scientific decision on how to utilize this data to simulate the plume of your accident. It's not easy. And whatever decision you make, you will be criticized. Why did you choose this one instead of the other one? So you have to be very, very careful. You are under a lot of scrutiny. And this is the wind direction. At some time, the wind direction, at some hour, the wind direction may be 180, which means from south, or 270, which means from west. Which one do you choose? How do you justify your choice under interrogation in front of a jury under oath? You have to think in advance all these things. Even if you don't work in litigation, if you present a paper to a conference, you may have very tough questions about what you have done, even if it's not a litigation. So it's a challenge. The next step is modeling. Already, we talked about that. I show you the movie, so I'm not going to do it again. Just want to mention that today animation capability are much, much better than 25 years ago, and we can do something very nice with Google Earth and with other animations. GIS is absolutely indispensable. If you have not used a GIS before, I suggest you invest. You don't have to be a GIS expert, but you need to know the basic of GIS, Geographic Information System, and what you can do with the GIS software, because it's absolutely essential. In litigation is indispensable, but also if you present results to a conference and you incorporate these results under GIS layers, that will be a very good idea. What we do all the time, we have layers of which we can turn on or off in our GIS. So you can see the plume, you can see the location of the people who are complaining, you can see the geographic features, the terrain elevation, the model simulation, the isoplet, everything is a layer. And you can turn on and off any layer. So you can superimpose automatically all this information. Is really, really good. We use it all the time. This was my first GIS visualization, very primitive GIS in the 90s. So I always start with the ugly one. So this was a fire in Baton Rouge, Louisiana. And these are all the people who complained about the fire. And again, I was able to show that based on my best opinion on meteorology and plume modeling, this is the trajectory of the plume during the accident. So you can see that that's another thing very good about GIS. Once you have the 5,000 points of the people complaining, and once you have the plume, you can ask GIS, please highlight the dots that are inside the plume. And the GIS does it for you. See, these are the people that are exactly inside the plume. So these are the people who may claim a higher impact than other people that are maybe 20, 30 degrees away from the plume, as we discussed before. So without GIS, this work would be impossible with thousands of people. With GIS, you do it in a minute. This is another example. I already showed you this, where my plume was able to show that identify exactly those that are inside the plume and those that are not. There's a zoom in of this impact. So this is the way we work. This is the way we operate especially in litigation. Our goal is to use the best available science to give our client the best results, and then they will decide how to use them. We are not attorneys. They will decide if they want to use our results and how they should be used and to present their case. Adverse effects. Which time is it? 7:45. Okay. So we'll finish at 8:10. Sometimes it's not enough to do your bloom modeling to provide the concentration results. Your client will ask you, what are the adverse effects? And so you open a new chapter. And you need tools that are different from what you have used so far. What are the adverse effects that needs to be quantified, simulated, assessed? Typical human health. Human health is number one. That's how air pollution studies started at the beginning for the protection of human health. So you need to be, typically, there are a level of concern established in the literature that should not be exceeded. There are two types of level of concern. There are concentration that below which you do not expect health effects, safe values. And there are concentration above which you would expect some health effect, adverse health effect. So the difference, if you think about it, the difference is important. One is below, no effects, and one is above, we expect effects. Maybe only on some number of people, not everybody. So these are initial values that you can use to compare with the results of your model. Again, there was an accident, emission of chemicals, you have done the simulation with your air pollution model, you know the concentration all over your domain. Now is the time to say how bad these concentrations are. And so are they above the existing level of concern or not? So you have to choose level of concern, and there are many in the literature. The one that seemed to be the most accepted are okay, they removed my link. Okay, thank you very much. Let me find it. Okay, so these are called the EAGLE, and they are acute exposure guideline level. So these are concentration. These are concentration that for every chemical, of course, that should be used to give you an idea of values of level of concern for acute exposure. Acute means long time, a short term. For example, a few hours or a day. Chronic is long term. For example, 10 years. Acute is short term. So here you will find all the definitions. EAGLE 1, the lowest level, that above which, okay, you see that's important. EAGLE are level of concern defined above which it is predicted. So if you exceed the EAGLE, it is predicted that some population may have adverse health effects. And there are 3 levels. Eagle 1 is the lowest, so the effect will not be very bad, practically, but there may be some effect. Eagle 2 is higher value. The effects are they may be serious, but not enough to block the individual from escaping. So you smell something bad, you can escape. Eagle 2 is not something that will make you faint. Eagle 3, even higher, is a level that can be life-threatening because it may be so high that you don't have the capability of escaping. You may be trapped in the location where you are. So, for example, this is just an example, chlorine. Chlorine is a gas that sometimes you have a situation where this gas can escape from industrial facilities. I've done a couple of cases of chlorine dispersion. And so these are the Eagle values that change 1, 2, 3 and change with the duration. For example, the Eagle 3, the Eagle 2 for a 10-minute impact is 2.8. But for an 8-hour impact is even lower, 0.71. Of course, the longer the impact, the longer the duration of your impact, the lower the concentration that is of concern. So these are tables, simple tables that can be used to compare with your model output and establish where in your region you can have an isoplet and you can color in your map the reason where Eagle 1, Eagle 2, and Eagle 3 were exceeded. That's what I do all the time. I choose a level of concern, and then in my concentration map, there will be a color area. If there is an exceedance, there will be a color area showing the area where some people could have been affected. Okay, let me fix this. So the next time I use this PowerPoint, okay. Other adverse effect, odor. We already talked about odor. And I think you know what you need to know. Let's see what this pointer is. Again, they removed it. It happens all the time. They change the location, especially government sites sometimes are a problem. They change their location and they don't allow automatic update of the pointer. I'll fix it later. Other adverse effect, damage to material. You may have corrosion. You may have deterioration of painting. Your home can have some damage on the walls. They need to be repainted. Surfaces, your car in outside your house may have some deposition of chemicals. The house need to be washed as a minimum. You have to pay for washing the car or any damage that you may have in your property, and also reduction of property value. This is a very interesting issue. You need a real estate specialist to work with your team to calculate the reduction in property value because you live in an area that has been affected by an air pollution accident. And, you know, some people will say, I'm not going to buy a house in an area that is affected by accident. So in theory, after an accident, you have a reduction in property value. It is a theoretical reduction, but can be calculated by an expert. And so this is something that maybe the industry will be obliged to pay to settle the case. Okay, so to do all these things emission meteorology, modeling simulation, adverse effect, you need computer tools. You don't do anything this day by hand, by pen and paper. Even simple calculation, even simple algebraical calculation are done with computer or with Excel or with MathCAD. So you need to use computers, especially for modeling of transport and fate of chemical, which is the main topic of our course. So each issue have its own set of equation, software, and one big challenge is to choose the right tools. Again, let me show you a few case studies. I've learned a lot from working in real cases, not just theory, and I think you can learn something too. This was, okay. This was a very interesting case. Very interesting, because it was a fire. We had several video of the fire. So when you have a video, it's good because you have a preliminary idea of the behavior of the fire. And when the fire is large, as I told you before, the plume is not going horizontal, or is going horizontal much, much later. The plume is going up. 99% of the plume is going up, and it will continue to go up because it's quite hot. However, be careful. This is the visible part of the fire. And this is a very important issue that many modelers missed in the past. This is the visible part of the plume, but it looks like there is no plume at ground level. That is not true. There is plume at ground level. If you are here 50 yards from the fire downwind, you will smell a lot of bad smell. But it's not visible because the only visible part is the thick black smoke going up, and it will continue to go up for 1 kilometer above the ground. So there may be the temptation to say, oh yeah, the plume going up, nobody's affected. And that's not true. A fraction of the plume, sometimes a good fraction, can be 1, 2, 3%, is staying at the ground, and it is affecting people at the ground. But it's not visible because you only see the thick black plume. But the real important fraction of the plume that is impacting people is that 1, 2, 3% that is not hot enough to be in the center of the plume. But it is on the borders of the plume. And you see here, look at the picture. You see all these little eddies. This is typically the portion of the plume that is on the border of the plume is directly in contact with urban air, with ambient air, and it's cooling down very quickly. So you may have 95% of the plume that is very hot and go up and up and up and up, but you may have 1 or 2% of the plume at the borders that cools down very quickly and stays at ground level. Sorry to blow my nose. This is extremely important because in all our air pollution modeling work, we are concerned about concentration at ground level, where people live. So when you study a plume from a fire, you have to be very careful, try to understand, look at the videos, look at the pictures, and try to understand, because only a small fraction of the plume is the one that you will be interested. The other fraction of the plume will go up, and maybe there will be some impact a day from now, 24 hours later, and 50 miles away. You don't really care. That impact is going to be very small. The region with the maximum impact is within a few kilometers from the fire, and is caused by a fraction that sometimes is very small, very small. So all your calculation need to be done thinking in your mind, I'm not dealing with the plume from a stack, I'm dealing with something else that is not as easy to simulate. This was my simulation of the plume in 2 dimensions, X and Y. And I use a loft, which is a plume model from a fire. This model is not distributed anymore. There are others, more complex models that can be used, but in this case was perfect. I was able to simulate the plume exactly in a very realistic way. Most of the plume goes up, but there is a fraction of the plume, there's a blue and yellow concentration, which is color coded, that remains at the ground level. What did the other side did? So this is what I did with a loft. The other side, the scientists working for the plaintiffs, not for the industry, had this. The other side used ISC, which is the father of air mod, very similar to air mod, is a Gaussian plume model, and he kept the entire plume attached to the ground because he's used the wrong model. He used a Gaussian plume model. A fire is not creating a plume that can be simulated like that with the Gaussian plume model. This is not the plume that we see in the picture. In the picture, we see something that goes up like I did, and not something that stays down like he did. So this is an example of how easy it is to make mistakes, using the wrong model for the wrong scenario, and then presenting the result to a jury, and you have the challenge here to explain to a jury why you are right and why he is wrong, which is sometimes is not easy. Another case study, it was a chlorine release in Baton Rouge, Louisiana. I've done a lot of work in Louisiana. I always tell them that Louisiana is the only place in the United States where I do not miss Italian food. Their food is very, very good. If you have a chance to go there, it's amazing. So there was, again, this is the Mississippi River going through Baton Rouge, and this is the facility, and this is a 3D visualization of the facility. The chlorine release was in the middle here. So you remember yesterday I showed you the modeling of the canyon, the pollution in an urban canyon. Here, my first comment to the client is that, well, we may need a CFD model here. We may need a CFD model, computational fluid dynamic, because there are so many buildings here that are affected that to do it right, I think we need a CFD model. But again, that's another lesson you learn from life. Sometimes you would like to do something, but you don't have the budget. So we didn't have the budget of a CFD model. So I thought about it, And I decided, well, I can still apply a Gaussian plume model with some uncertainty, but still. My conclusion was that the effect of the building is more dispersion, more dispersion. More dispersion means more opening up of the plume. More opening up of the plume means lower concentration. So by not using CFD, I'm overestimating the concentration. And I thought, that's fine. I'm not working for the plaintiffs. I'm working for the defense. So it's okay to overestimate. That's another thing that you need to learn when you work for clients. You need to know the interest of your client. And you should try always to overestimate and be conservative if you work for the defense. So they cannot tell you, oh, you are working for the defense, so you are trying to minimize air pollution. They could have said that. Oh, yeah, you chose a CFD because you wanted to have a lot of horizontal and vertical diffusion and spread the plume to have lower concentration. They could have said that. So I felt comfortable in using a Gaussian plume model, which of course can be done with a lower budget than a CFD. And these are my results, which were very favorable, very favorable. Concentration where, fortunately, the fence line, it was far enough. Let me see if I have a scale here. Yeah, I have a scale. The fence line was about 200 meters. So if the leak would had been here at the fence line, perhaps it would have been different. But the fence line was 200 meters away, and I believe the residential area was away from these isoplates. So the conclusion was, yes, we had a leak. Yes, sorry, we had a concentration that escaped the fence line of the facility, but in terms of damage, health impact, no, we did not have, we should not have had a health impact because the modeling that we have done using the best available science and also being conservative, as I told you before. Okay. Are there any questions? We talked about many issues related to litigation. I hope I didn't bore you, but you may be involved in the future in cases like that. And even if you're not involved in litigation, there are rules here to learn, to be very careful, very accurate, very honest, whatever you do. So are there any questions? Very good. So 808, I think that's the end of lesson 2. And we will continue lesson 3 with this presentation and some other stuff. Okay, I'll see you in 10 minutes again. Thank you. Very good. Can you hear me well?
Yes.
Very good.
Yeah.
Oh. Okay, so there is some chat here. Okay, I will read it later. So we were talking about how careful you have to be when you do modeling and choosing the right model. In particular, the fires are a big challenge. And by the way, this is a case also where my client allow me, generally they don't like to share the technical report, but in this case, I was allowed to put the technical report here on my website. So this is an article that we published describing the modeling work that we did and the concentration that we obtained. So it is available. All right. Day 3. So we were here. Beverly Hills, Bloom modeling, Bloom. Okay, another couple of examples that, again, I hope they are useful for you to put things in perspective and give you some ideas of the real world that exists that requires the use of air pollution modeling. This was a case of a traffic collision. There were cars driving on this road. They were driving from right to left, and there was a big collision here. And the problem was that at the time of the collision, there was activities by large machines collecting almonds. These are large machines that make a lot of noise, a lot of vibration, and a lot of dust. And they go up and down in this field collecting almonds. So the cloud of dust obscured the vision of the drivers. And so the dust was the reason of the accident, according to the drivers.
It was responsible.
Say it again.
It was the cause. It was responsible. I mean,
Yeah, they tried to blame correctly, I believe. They were driving quite fast too, but they were trying to give the entire responsibility of the accident, and was a very bad accident, to the dust created by these machines. And it was interesting because they had two machines, one going up and down here, very close to the road, and the other going up and down here, not close to the road. So and there were two different companies. So the challenge was to attribute the responsibility to one of the two companies or to both. And I was hired by people who asked me, can you make a case here? Can you run a model? Can you tell us which of the two companies, if any, is responsible for the dust? So I did all the work that we described before: emissions, calculations, meteorology, where the wind is blowing from. The wind was coming typically from northwest. So yes, the wind was taking the dust from the agricultural field toward the road. And I calculated the concentration of the dust from the two operations. Of course, the machine closer to the road is giving a very strong, high concentration, but a narrow plume. And the machine far away from the road is giving lower concentration, but a larger plume. these were my results. I presented the result and they say, thank you very much, but what we need, I want to see the visual impact of the dust. Sorry, is there a question? Okay, if there are no questions, please mute the microphone. Okay, so the goal here for my client, he didn't really believe that the concentration was the answer that he needs. He needed a visual impact from the driver perspective. He wanted to see what the driver saw. So we were asked, can you show the actual, sorry, can you mute the microphone? Okay. Very good. So the next step was the big challenge. I've never done this before. And it was to create a synthetic plume showing the visual impact of these two plumes. And so we started by taking a picture of the road from right to left. So this is the picture on a good day with perfect view. And then this was the boring part. Each pixel here, and we are talking about probably 1 million pixels, each pixel must have a distance, must have the number representing the distance. So this pixel must have 10 meters, this 20 meters, 30 meters, 50 meters, 200 meters, and so on. So there was a manual work here that was done for each pixel to attribute, calculate a distance. And then,
Can I ask you something?
Yeah, certainly, go ahead.
Can you tell us how we can do this to apply distance to a picture? In each picture.
I cannot hear you very well. Can you repeat your question? Or you can type it to me in the chat if you want.
How we can apply different distance in each picture? In this picture.
Okay. Well, we have a picture. Each picture has say 1 million pixels. A pixel is every point, every dot in the picture. And then we have a file, a numerical file with the X and Y of the picture. Any X and Y of the picture is 1 pixel. And each 1 pixel has a distance. So you're going to have X, Y, and the distance. So you have 1 million lines with 3 numbers for each line, X, Y, and the distance. This has to be done manually, cannot be done automatically. So we have an Excel file or a text file in which every X, Y point in this picture has a distance from the observer. So 5 meters, 10 meters, 20 meters, 100 meters. So we know for each pixel, each point, the distance from the observer. And then we have the plume here that was calculated using, I think we use air mod or ISC. We use a Gaussian plume model. So each each pixel has a plume going through. You see, the observer is here at the end of the street. The observer is looking in this direction. So this pixel here should contain the impact of the entire plume. How do we do that? Well, we calculate the trajectory from the observer to in this direction, and we have the integral, the sum of all the contribution of the plume. We apply some function of calculating the visual impact of the plume based on the integral of concentration from low concentration here, higher, 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 and then lower and lower. And what we obtain is this, a synthetic cloud. So it's a lot of work. It's a lot of work. We use the three-dimensional concentration here to calculate the visual impact. In this case, is a sort of a gray area. And if you look at it, it's very realistic. It's very realistic. Here, there is no impact because the plume, we are looking at down level and there is very little plume. But here, there is the integral of the entire plume. So there is a large impact. And then we move here and there is a lower impact because there are lower concentration. Everything makes sense. And above the plume, there is no impact. I see this because the plume is limited in Z, in the elevation. So it's a lot of work, but the results were quite believable and applicable to this case. We have created an artificial, a synthetic plume representing more or less, with some uncertainties, the visual impact of the driver passing through this cloud. And we can do that for this plume far away, but larger and smaller in concentration, and this separate plume, which is closer and it is narrow, but higher concentration. We can do both. Here is the plume that is very close to this road, and here is the plume that is not close to the road. You say, I don't see nothing. No, there is something. If you compare the original picture here with the picture of the faraway plume, you see that there is some impact here. But of course, this impact is nothing in comparison with those created by the machine that was closer to the road, which we knew since the beginning, but now we can prove it. So this is an example on air pollution modeling application where concentration results are not enough. You need to do more. And what we did was to create synthetic plumes, proving that the only machine that was really affecting the visibility and perhaps contributing to the car accident was the machine number one, working very close to the road. So something different that allow us to learn more about atmospheric visibility and visual impact. A last example is that was a big project. They spray. We are in south central Idaho, near the border with Canada, in the United States, and there was a spray of a herbicide. The herbicide name is Oust. Is a very potent herbicide that is used, in this case, was used to kill the vegetation in order to minimize the future risk of fire or wildfire in the following months. So they sprayed this herbicide killing the vegetation with this very powerful chemical. And what happened, unfortunately, is that a lot of herbicide remain in the ground, continue to be active, and we had dust storms after the application of pesticide. We have several high winds and dust storms. So a lot of dust was picked up from this area and carried east by the high winds. Even 100 miles away, this is a long-range study of resuspended dust. And this dust was contaminated, still contaminated with active herbicide oust. And so this dust deposited 10, 20, 50, 100 miles away and damaged, according to the owners of these agricultural fields, damage these farmers' fields. So there was a big litigation against the people, the State Department of Agriculture, who did who ordered the spray, and the manufacturer of oust. And we had different modeling experts presenting different results of this contamination. So this is an extra challenge. It's not just emission and deposition. Is spray, deposition, resuspension, transport, and another deposition. So it's a very complicated set of phenomena that need to be simulated. And these are my results. And for 2 different years. And in both years, we were able to show that, yes, there was clearly a high probability of transport and deposition of contaminated dust, even 100 miles away. In this case, too, the client allowed us to publish our report. So again, if you want to examine what we did and see the type of work that is typically done in this situation, which is more complex than the typical situation, you can give a quick look to my report. And let me see if there is anything else I want to say. We use CalPAF. We have no choice. This is a long-term, long range, and even long-term simulation. Air mode would have been totally inappropriate. So CalPAF was the only model capable of doing this. We had measurement of oust at different locations, so we were able to sort of validate and calibrate the model. I already showed you the results, the final results, but of course we had we presented the results for every day. Every dust episode gave different. We had several dust episodes, so we have several combination of the position of contaminated dust. And finally, we sum up everything together to give the total amount. Sometimes the wind was not blowing east, but again, at the end, we did the entire cumulative deposition, taking into account all the dust episodes. Okay. So the conclusion was, yes, the people who complained for damage of their agricultural production had a point. There was a high probability that they were correct. There was a high probability that the damage was caused by a spray done earlier, tens of miles away. The modeling approach was convincing, and there was a big refund that was given to the farmers. Again, this was a major case, a lot of interest by the media, television networks, and news. Okay. All right. So we have time to go back to some material that I skipped yesterday. We are going to finish at 9:20. Okay, so we have quite amount of time. So day 2, I think we stopped here, talking about adverse effect of air pollution. And all these adverse effects can be modeled by a certain extent. The reason I say to a certain extent is that transport and diffusion of chemical in the atmosphere has some uncertainties. Then when you move to other phenomena like deposition, you have even more uncertainties. And then when you move to consider the adverse effect of air pollution, you have another set of larger uncertainties. So the uncertainties are accumulating with all your simulations. So the more ahead you go, the more you have to be careful about your results. But yes, there are formulas and models that can be used to simulate and quantify virtually any adverse effect of air pollution. For example, human health is number one, and one typical calculation. And by the way, I want to tell you, most of these calculations are relatively simple. You don't have complex things like the Navier-Stokes equations for CFD. Most of these additional calculations are algebraical, simple algebra, something that you study in high school, with some exception, of course. But in general, we deal with a relatively simple formula that still we have computer software to calculate. One important formula used all the time is used for chronic long-term health risk assessment, is the calculation of the dose. What is the dose of chemical that was inhaled by a person during a lifetime? Typically, a lifetime is 70 years. And over 70 years, you can imagine a person is driving, working, sleeping, going to the movies, walking in the street, exercising, running, whatever. So each scenario on each day of these 70 years has a different concentration exposure. So how do we calculate the dose? By making simplification, by making assumption, like I show you in the Beverly Hills case. We look at the lifestyle, the typical lifetime of several people, to establish how the fraction of time spent in different environment at different time. For example, we knew where they lived. We had the address of all their homes for 20, 30 years. So we were able to assess the possible concentration impact at those locations when they were outside. And you can do it. You have to do a major approximation, but you can do it. You start with the person, you look at the lifetime, 70 years, you look at the lifestyle, you look where they lived, what they did, and more or less, for each chemical of concern, you may establish the concentration of chemical that they have inhaled. Then you know the concentration, don't forget, is mass over volume. Mass over volume. Then you know the volume of air breathed per time. You know the inhalation rate, typical of a person. So is a volume. So concentration divide volume by volume. Concentration is mass over volume by volume. You have mass. The mass of the chemical inhaled. Multiply by time, the different time, 1 hour here, 1 hour there, 8 hours sleeping, 2 hours exercising. You combine this number with their lifestyle at the workplace, indoor, outdoor, and you have the final dose. Dose is mass per time. And this is the mass of pollution inhaled. So once you have this magic number, you can compare with levels of concern. And of course, you have to be careful because the concentration inhaled could have been caused by different sources. Some are natural. This person was cooking at home. When you're cooking, you create, as a minimum, when you burn natural gas, you create NOx. So you must take care of all these things: exposure, inhalation, different sources, and developed a final dose, the mass of pollution inhaled, and know which one is caused by emission A, by company B, and by different sources. Once you have the dosage, the next step is to choose dose-response relationships. And again, these are models, simple models, that correlate the dose with the probability of getting cancer or the probability of getting other diseases, non-cancer, but there are formulas like that. Dose probability. So if the dose is high, you will have a high probability of developing, let's say, higher probability of getting cancer. If the dose is low, you will have a low probability of getting cancer, but still is non-zero. And this is a very important issue. Many times we use dose-response relationships that are linear, and they start from the point 0, 0. What happened? What happened is that this is very, very questionable, very questionable. Both the linearity and starting from 0, 0 is very questionable. That means that if you smoke a cigarette a year, you have a non-zero probability of getting cancer. Very low, but it's non-zero. And if you multiply by 1 million people who smoke 1 cigarette a year, you will find that even a small probability multiplied by a large number of people will give you some people that should develop cancer smoking 1 cigarette a year. This is a silly example, but just to show you that you have to be careful with these things. If you start from 0, you are practically saying that even insignificant doses of air pollution can cause some cancer. And that probably is not the case. Of course, I'm not an expert in toxicology, but there is some common sense here that should be used. But again, if you only use those response relationships that are linear, start from 0, you may overestimate the cancer response, according to many. So many people prefer a situation where you have a curve like this one, in which from 0 to here, there is no response. Practically, there is a minimum dose that should not create any probability of getting sick. And then maybe the dose response is not linear, but maybe higher at the beginning and then going flat later. You know, these are all studies that have been done by toxicologists, mostly with animal experiments, because again, whenever they tell you that 2.4 million people die for air pollution every year, as I told you before, there are no bodies, there are no corpses showing that this is true. These are just calculations done with animal experiment. Sometimes I read about those experiments, and frankly, it's hard to believe that those animal experiments on mice can be projected to human. Is very questionable. I'm not the only one saying this thing, that perhaps we exaggerate, we overestimate it. It's very questionable. And especially when you look at the average life on Earth that has been constantly increasing with time. And so these air pollution effects should be a minor change in this curve. It's hard to discriminate between air pollution, indoor air pollution, outdoor air pollution, and other problems like diet, obesity, smoking, and so on. I think it's very difficult. I already told you that, but I wanted to insist on this, to be very careful about this projection from animals to people. This is not like car accident. Car accident, we know, we have the number. And we have the statistics, we have everything. Here we are on a gray area. However, closing this parenthesis, there are formulas in the literature that allow you, once you calculate the dose, which is not easy to calculate, but once you do that over a 70-year period for a person, you can establish the probability of getting adverse health effect through these simple formulas, linear or non-linear, of dose response relationship. There is good software that can help you with this, especially in California. I think California is ahead of the federal government, I believe, in providing good software for health effects. The HARP software is what people use here. It's called Hotspots Analysis and Reporting Program, HARP. Has been around for a while. I think now they have version 2 that is distributed by the California Air Resources Board. And by the way, in addition to the EPA, which has excellent websites dealing with air pollution, also you can consult the California Air Resources Board. They have a lot of material, software, programs, publication, resources. It's really amazing what they put together here. It's excellent teaching material. So HARP is a software that can help you. Can help you a lot if you're dealing with health assessment. It has 3 programs, 3 modules. The emission inventory, because you need emission to run the model. The air dispersion modeling tool, which is mostly based on air model. So it's a Gaussian plume model. And then the risk assessment module. So everything is in the same software called HARP. So it's relatively easy to use. This will be a good investment of time for those of you who continue to work in air pollution, to read more about HARP and be able to use it. And there are also courses that you can follow with that you have so-called hands-on courses. It's not like mine that I give you just an introduction to everything. These are courses that go through one particular piece of software for 3 days, and you really learn how to use the software. So HARP is a good choice in California, but all over the world, I believe, to study the health effect of air pollution. And the user's guide is here. Maybe we can give a quick look. Yeah, they have version 2 now. Let's give a look just at the table of contents to see if there is any comment that I may add for this introduction. This everything I told you before. We need to know how the pollution moves from point A to point B. We need to know the breathing rates to calculate the dosage. We need to know the frequency of exposures in different locations at different times. We need to know not just how much we inhale, but other pathways. For example, dermal. You can touch air pollution, or air pollution can deposit on your hands or on your skin. And you can have pollution through the mother milk, because pollution has entered the system of the mother that is feeding the baby. There are so many pathways. Drinking water. You drink water, there may be chemicals that are that remain in your body. So this software is calculating not just air pollution, but all possible pathways of pollution entering your body, of chemical being retained. The beef that you eat, the milk that you drink, pig, chicken, eggs, cancer and non-cancer effect, different formulas. Okay, so you can see it's a very comprehensive piece of software that is used in California, in other places, to develop an estimate of the adverse health effects on humans. Another useful publication is this one. Is the is a guidance manual for preparation of health risk assessment. So it's more information, more guidance to calculate the effect of air toxics. Again, let's give a look to the index to see if there is any comment. Okay. Very similar issue to what I have described before. quantify the source, quantify the terrain, quantify the receptor, the meteorology, do the air pollution modeling. Here they use a air screen, which is exactly the model we played yesterday with, or air mod. The calculation of the carcinogenic potency with the relationship that we discussed before. Cancer and non-cancer indexes to see if you exceed certain level or not in a certain area at a certain time. So similar to what I did before, but this is more dedicated to hotspots, to try to identify some region where you are more concerned than others, typically very close to factories, especially factories that emit a highly toxic pollutant like dioxin, like chromium-6, lead, and location close to highways where you expect more air pollution from the traffic, especially diesel particulate matter, which I told you before is the #1 cause of cancer risks in California and probably all around the world. Okay. This is another set of slides similar to what we have discussed before. This is the formula that I show you, and the dose-response relationship we already discussed. This is quite useful to see how do we do health risk assessment. Is basically 4 steps: identification of hazards, exposure assessment, dose response assessment, and finally risk characterization in terms of probability. Every risk are expressed as probability. There is an example here for benzene. Benzene is one of the most frequent chemical used to do health assessment, especially in big cities like Los Angeles. So you can look on your own about this example for benzene to see how this calculation work, the sequence. Okay, I think that's enough. That's enough. And we have about 10 minutes. Do we have any questions? We don't have questions. I'd like to say a few words. We have 10 minutes on other adverse effects. Again, everything can be expressed in mathematical terms. So it's part of our modeling approach, our modeling knowledge. We have to be aware, at least on a superficial basis, of all these mathematical formulations. There are adverse effects on animal by air pollution. If you want to know more, there is this nice web page from Canada, the Environmental Agency of the Canadian government. And there is more information about damage on animals. Plants, of course, there are a lot of studies of the effect of air pollution on plants. There is an entire book, well, probably more than one, but this is the one that I think is the best, or at least the one that I have examined sometimes. There are effects of air pollution on plants, both of gases and particulate matter. One of the most known effect is acidic deposition. You remember acid rain was in the news for more than a decade, and it's still a problem in some situations. And of course, it's a big problem when you apply pesticide, like the project I mentioned before, where an application of a herbicide damage vegetation and agricultural products 50, 100 miles away. So there are a lot of studies, a lot of quantifications, some formulas that relate air pollution to damage of plants, damage of agricultural products. There are some products that are very sensitive to chemicals, like I've been working in many cases related to strawberries, blueberries, tomatoes. So there are plants and products that you have to be very careful if you spray pesticide, in the next field, because there can be a drift. That's how we call it, a drift of pesticide from the target field to other fields that are more sensitive and can be damaged. Again, in the United States, there is a lot of litigation in when this situation happen. Visibility. Visibility is a problem. I show you a case of a car accident a minute ago, but in general, visibility is an issue because any impairment of visibility is a problem for tourism, for enjoyment of life, enjoyment of what you see outside your home. You don't want to see black plumes. You don't want to see haze or fog caused by industrial emission or traffic. So visibility has been a major issue, especially in the United States. Other countries are not that concerned. They are more concerned about human health effects. But in the state, visibility has been a big issue. In fact, there is an entire visibility section in the EPA website, visibility and regional haze. One of the reasons is that in the United States, we have, one of the main beauties of the United States are the national parks. You may go to Italy to visit Venice or Florence or Rome or Pisa, the monument, but many times when you come to the United States, sometimes it's a good idea to skip the cities and go directly to the national parks. At least that's what the recommendation I give to my friends when they visit the United States. I don't find the cities very excited, with some exception, but the national park are absolutely fantastic. Grand Canyon, Bryce Canyon, everything. Yellowstone, Yosemite. Okay, so visibility problem in the national park is an issue. When you visit a national park, you would like not to have regional haze. And some regional haze may be caused by natural problem, relative humidity, some emission of hydrocarbons from the forest, but other problem may be created by anthropogenic emissions. For example, I studied the effect of a huge power plant in Arizona near the Grand Canyon. And this was a long time ago, in the 90s. And we did a lot of study of the plume, of SO2 plume from this power plant. It was the Navajo power plant in Arizona. And this SO2 plume could travel in certain conditions to the Grand Canyon. And by the time it travels to the Grand Canyon, some SO2 has been transformed into sulfates. Sulfates, SO4, are small, very small particles, and small particles are quite efficient in creating visibility problems, even at very low concentration. Sulfate concentration that are absolutely no problem for human health may be a problem for visibility in the Grand Canyon, because even a small amount of pollution can reduce the visibility from 100 miles to 30 miles. The initial impact is quite high. So you may say, well, 30 miles is still quite a lot. Yeah, it's still quite a lot. But if you see a picture of the Grand Canyon on a day with beautiful visibility, you don't want really to make it bad or to damage that type of view. So visibility modeling is an important issue, and there are models developed by the EPA that can help you. And also today, the grid models that we discussed yesterday, for example, CAMEX and the other photochemical model, also include visibility routines. So today you can use the photochemical models, the grid model, and they allow you to also to simulate the visibility impact. What else can I say about visibility? Well, I will say that visibility is part of the state implementation plans. We didn't talk about state implementation plan. It's something that happens only in the United States, but there are similar programs in other countries in the world. State implementation plans are plans that every state in the United States must prepare, typically every 5 years, to tell the EPA what are their problems in air pollution and how they plan to improve them. And the EPA will review these plans and will accept them or not accept them. The EPA may say, no, that's not enough. In the next 5 years, you have to do more. Otherwise, so state implementation plans include visibility. So every state have to tell the EPA what are their problems with air pollution, what are their problems with visibility, and how these problems can be addressed and improved in the next 5 years. So visibility is a high level of concern in the United States. Okay, there is this brochure, which is quite nice. I looked at it before. Explain to the general people, this is not for scientists, but is useful. Explain how air pollution affects the view of a natural view. And this is the figure. This map here shows where we have more problem of visibility and less problem. Of course, more problem in the east than the west, because visibility impairment is related to the density of population, among other things. So, for example, the east is more populated than the west, and Los Angeles, of course, here is more populated than the rest of the west. Okay. This is a nice figure to remember. Is the basic concept of visibility. You have solar radiation, and part of this solar radiation is reflected, and that's what we see. We see the light reflected from an object, any object, and part of the light is reflected away. Part of the light is reflected toward your eyes when you look at an object. But this light that goes from the object to your eye can be absorbed by some air pollution, so it disappears, or can be scattered, or can be absorbed, so disappear, or additional light can be added by the light of the sun that is scattered toward your eyes by air pollution. So air pollution has two main functions: removing some of the light that you want to see and adding some of the light that you don't want to see, because it's scattered light that actually damage the view of your object. So absorption, reflection, scattering. These are the phenomena that you are concerned with. And particle, gases may be important too, but most of the time, especially in rural areas or in the national park, the particles, the small fine particles, are the most effective in damaging your view. Okay, so I think we can interrupt here and restart for the last lesson of the last day at 9:30. Bye-bye. Very good. We are at the end, last lesson of the last day. Can you hear me well?
Yes, everything's fine.
Very good. Very good. I hope you enjoyed the course. I don't know if some of you want to tell me if they intend to continue to work on air pollution and how they are going to use this material. If you have some comment about your future, I'd like to hear them. Very good. I was hoping to take advantage of your talking to use my candy. My throat hurts after 3 days. I talk too much and sometimes too fast and too loud. But I made it. I was able to make it till the end.
Mr. Zanetti.
Yeah.
Yeah, I have a question.
Go ahead.
So I am working on a project in which I have a data set that is made up of meteorological variables such as temperature, wind speed, wind direction, and I have to predict MP10, particulate matter 10, the pollution.
PM10.
Do you know? Yes. Do you know of any statistical model or any algorithm, maybe from machine learning or something that I can use to predict PM10 from variables?
Well, if your goal is the prediction and you have measurement, first of all, are you talking about prediction a few hours ahead or days ahead, or what's the time scale?
24 hours ahead.
24 hours. Okay. So your problem is the typical problem that we have in urban areas, especially in urban areas, that I have measurements, and I have measurement until now. For example, now is 9:30 a.m. in California. So I have measurement of PM10, hourly measurement, I suppose.
Yes.
And so now is 9:30. So I have the existing measurement until now. How do I do in terms of forecast? Forecast in the next few hours, the next 24 hours. Well, there are several ways. There are deterministic ways and statistical way. I've used both. For example, statistical ways are the ARMA or ARIMA models that we discussed, I believe, on day one. These are Box and Jenkins model, they are also called. They are purely statistical. You look at your time series until now, until 9 a.m., and by purely statistical method, you try to calculate the evolution in the next few hours. They are not bad, but they are limited. It's completely statistical. There is no deterministic component. So it's just a way of looking at the past and hoping that the past will reproduce itself, the same trends, the same cycle in the next few hours. Sorry. The alternative are the deterministic model, not the statistical model, like the one that we have discussed. Hermod, CalPAF. So if you have the emissions of PM10 in the area, you can run the model. You can run a particle model that gives you results every minute. But again, this is a model. If the emissions are not correct, the forecast is not going to be correct. Also, you need to know the emission in the next few hours. Right now it's 9 o'clock. If you want the forecast in the next 24 hours, you need to know emission and meteorology in the next 24 hours. So it's a challenge. The best way is to combine the two together. And this has been done by some people using techniques like Kalman filters and so on. Practically, you want the best of both worlds. You want to have a deterministic model, like a particle model, with the forecast of emission and meteorology, and then you want to correct this forecast with the measurements. It's not easy, but it has been done in the past to combine a statistical model like in ARIMA with a deterministic model like LAP model, the particle model. Send me an email to remind me, and I will try to dig out some of the papers I've seen in the literature before. But it is a challenge. It is a challenge.
Yes, thank you. You said, what was the name? Kalman filters?
Kalman filter. Kalman. Kalman filters.
Okay.
Yeah. I think there is something in my book online. Just a second. In my 1990 book online, there is something, I believe. I should put the title. Unfortunately, these are images. I cannot search with keywords. Statistical method. Here we are. I've done Kalman filterings a long time ago, but the methodology should be has not changed. So there is some description here. So in my 1990 book, which has been referenced before, you will find in the material I send you, you should find the link. There is a discussion, only 2 pages about Kalman filtering. So send me an email to remind me, and I will send you some other pointers.
Okay,
Okay.
sounds good. Thank you very much.
You're welcome.
Oh,
And by the
Prof.
way, go ahead.
No, what was that?
Yes, Prof. Yeah, can I start?
Certainly, go ahead.
Yeah. Yes, yes, Prof. I think I have similar problem with the last speaker. I'm also working on a project, like I told you, I'm modeling particulate matter air pollutants here in Malaysia.
Yeah.
And I have a data set for both PM10 and PM2.5. And I'm deeply into statistical modeling using ARIMA and ARFIMA.
Yeah.
I'm the second year of my study, sir. So I need something that I can improve my project with, like the air mode modeling you talked about and the CalPAP model. The only challenge is I don't know how to make use of these models. And I think it is going to be good for me having, I already did a lot using statistical modeling. If I can have corresponding deterministic modeling, those statistical modeling are purely stochastic modeling, as you know. So if I can have deterministic modeling, and I think that will really help me a lot. And then secondly, sir, I don't know, that receptor modeling you've been talking about, I don't know if I can make use of the measurements that I have for PM10 and PM2.5 to determine the percentage contribution of pollutants to it. I think that one will also help. But I don't know whether I can make use of the measurement to do any receptor modeling or not. These
Very
are my
good.
challenges.
Send me an email to remind me, so I will reply to you in a few days. And thank you for this question, because something I wanted to tell you is that as part of this course, I will be available to you to spend some time to help you. You know, I'm talking about 5-10 minutes here and there in the future. Don't hesitate to contact me with question or request, and I will always be available to help you with suggestions and material. And of course, if you have a major project and you want my help as a consultant, also I am available. That's what I do. I give courses under the umbrella of the EnviroComp Institute, nonprofit, and I do consulting under the umbrella of my corporation, EnviroComp Consulting. So I will be available for anytime you want for short help, and also for more substantial help as a consultant, if appropriate. Also, if I travel in your area, I'll try to remember to let you know. Maybe I can stop by and give a seminar. You know, I'll try to keep in touch with you, and you try to keep in touch with me if you need anything.
Okay, Prof. Thank you very much. I really can't thank you enough. Thank you very much, sir.
Very good.
Thank
My
you.
pleasure. I really enjoy interacting with new people and giving courses, especially interacting with young people, and try to make them save time. You know, my generation has to struggle. I started working in air pollution in 1971. We had no books, practically. We had very few papers. We didn't have university courses. We didn't have environmental departments at university. We had nothing. So we were the pioneer, and it was exciting. And now if I can help you, saving time so you don't have to struggle the way I struggle, I will be very happy. The last thing I'd like to show you, I always skip this slide as the last because there are so many topics and so little time. There are so many things that we could talk that I had necessarily to skip. Inverse modeling. Inverse modeling is when you have measurement, and from the measurement you want to calculate the emission rate. So receptor modeling is a type of inverse modeling. Tracer experiment are a type of inverse modeling when you have a tracer and you measure the concentration and you go back and try to estimate the emission rate. So I give you a pointer here. That's all I can do. Litigation modeling, we talked a lot about litigation, but here, for those of you who may be involved, I just want to point out a reading guide. And I wrote a couple of articles in 2001 and 2019 on the challenges of working as a scientist in litigation. So if you are involved in litigation in the future, you may want to give a look to, for example, this article, I think was a short article of a guideline to scientists about working on litigation. That is not easy. Just a list. Indoor modeling, we spent very little time with indoor modeling, is a science on itself. COVID simulation, COVID modeling, mostly indoor, is interesting. I have a presentation here, which is interesting. Emergency preparedness and response, we talked about that, but there is more stuff here. Pesticide application, that's another issue that, what do we have here? Yeah, pesticide application is quite a challenge. Pollution sometimes, the spray material sometimes does not go where we want it to go. And so there is an entire chapter here of modeling of pesticide application, deposition, and drift. So if you are involved in cases of agricultural problems, pesticide, read this chapter, is quite well done. Visibility modeling, we talked about visibility modeling. There is more material here. Receptor model, we talked briefly. And landfill modeling is quite interesting. This gives you an idea of the emissions from a landfill. Just look at the order of magnitude of the gas flak. Isn't that amazing? We have 4, 5, 6, 10 orders of magnitude difference in the gas flux from a landfill. You can imagine how the difficulty of simulating the emission from a landfill when the emission can change by a factor of 1 million. 1 million. So it's a challenge. It's a challenge. Okay, that's all I wanted to say. Let's keep in touch. You have my email. Thanks again for attending, and good luck.
Thank you.
Thank you very
Bye-bye.
much.
Thank you very much.
Thank
Bye-bye.
you.
Bye.
Bye.